going to continue with the second part of 11.2. Okay, this time we're going to talk about harmonic series and test for divergence. Okay, in part A, what did we talk about? We just talked about the last time. The telescopic series. What else? The geometric series, right? Okay, good. Okay, good. Now it's harmonic series. Now, where does the name here come from? Harmonic, right? This will remind you of this. The song is in harmony, right? Harmonic, right? Okay, the music, right? I think long ago I was watching cartoon. Okay, it was having something Donald Duck or something, and it has is about math. And what he does here is he went to this kingdom of math, and then he practiced a series string. It's like this. It's 1 and then 1/2, 1/3, 1/4, and he played those strings and to practice string, and the song that it produced is in very harmony, and so that's why I think it's called harmonic series. Okay, so if you don't see anything musical, and that's because you're not listening to the number. Okay, so you're listening to the number, and they're going to have a harmonic sound. Okay, all right. So the name comes from this. So this series here is 1 plus 1/2 plus 1/3 plus 1/4, etc. Continue this way. Okay, what do you think about this? This is called the harmonic series. Okay, this the one and only one harmonic series. Okay, it's called the harmonic series. So, do you think it's going to sum up to a finite number? What do you think? You suspect that it sum up to a finite number, right? So if you add them up, would that be a finite number? Say you save $1 one day, you save $0.50 a day, and a third. Keep on doing that. If you live forever, then that's the question, right? Okay, some people say maybe it added to a final number. Some people say maybe, may not, right? And now let's prove it. So the proof over here is a little bit, it's a little bit clever. The way they do it, instead of just add the first and turn, they add the first 2 to the end turn. Okay, 2 to the end turn over here. So first time they add the first turn. So that's just 1, right? S1 stands for the sum of the first turn, which is just the first turn, which is 1. Okay, the second one is S of 2 to the first power. Okay, the second one, the next one is X to the 2 to the third power, 2 to the second, and S to the 2 to the third power, which is S8. So we're going to continue this way and look at S to the 2 to the n. So S of 2, which is the sum of the first 2 turns, so it's 1 plus 1/2, right? Agree? And looking at this, S4, okay? So they skip S3, okay? So only looking for S4, okay? And then the next one S8, and then the next one is S to the 16, S of 16, etc. So S of 4 here, you're going to group these two together, this last 2 chains. 1/3 plus 1/4. Both of them, you're going to compare that with the turn that's smaller, 1/4. This is greater than 1/4. So certainly this is greater than 2 times 1/4. Do you agree? Right? Okay. Yes. Okay. It's greater than 2 times 1/4. 1/3 plus 1/4 is greater than 2 times 1/4. Right? 2 times 1/4 is 1/2. So put this together, right? So this one here, if I replace it by 1/4, that will make it smaller, right? So this is going to be greater than 1 plus 1/2 plus 1/2, which is 1 plus 1 over 2. 2 over 2, yes. 2 of this. So 2 over 2. So 2 over 2, right? Okay. Now the next one, S of 8. So you skip a couple of terms in between. So you consider S of 8. Okay. Now this time we're going to group these two together. We know this is greater than 1 half. This time we're going to group the 4 terms over here together. Each term here is going to be greater than or equal to 1/8, right? So you have 4 of this. So it's going to be greater than 4 times 1/8. Because if you replace each one of this by 1/8, then it's going to make it smaller. So that is greater than 4 times 1/8, which is 1/4, right? So this is greater than 1 plus 1 half, plus 1 half, plus 1 half. So that's greater than 1 plus what half? 3 half, right? Okay, good. So that's 3 half. Okay. Now continue in this pattern. Can you guys take a guess? If I take the partial sum of the first 2 to the n term, that's greater than 1 plus what over 2? N over 2, right? N over 2, you got it. Okay, so that's n over 2. Okay. If you let n go to infinity, what does n over 2 go to? Yeah, it go to infinity. Yeah. So we know that if you sum the first 2 to the n term, and let n go to infinity, which means you get more and more terms, then the sum is going to go to infinity, right? So if you try to think about the picture, if you add 1 and add 1 third, 1 4, 1 fifth, etc., you get the number actually goes to infinity. So if you live forever, one day you save $1, $1, one day, every day you say that, actually you can save to infinity. Okay? So, all right. So looks like some people say, this is a little bit counterintuitive, right? Looks like you keep on adding something smaller and smaller, but it still adds up to infinity. And this is one example. Okay, so you keep on adding that, but it still adds up to infinity. It's really slowly going to infinity, but we prove it. Okay, so it is true. Now you just need to remember this result. The harmonic series diverge to infinity. So let's put a star here, means that's an important result. Remember, harmonic series, what's the harmonic series? It's a series that has 1 over n as a term and go from 1 to infinity. It diverges to infinity. So the harmonic series is the one that make beautiful song, beautiful music, and it diverges to infinity. Okay, so you hear that. Another way to prove this harmonic series diverge to infinity, later on you can show using the integral test. Okay. Now, in the past we talk about 1 over n, right? Like this. This is something called the P integral. Do you guys remember? Let me give you a quick review. Okay. What's the P integral? Okay. So integral of 1 over x to the p power dx. X go from 1 to infinity, and this is called P integral. Do you guys remember when will P integral converge? Converges if and only if P is what kind of number? Is greater than 1. Okay, if greater than 1. Okay, for example, say this. 1 over x to the second power. Okay, or 1 over x to the 1 plus 1 power. This one. Okay, for example, then it's going to converge. Okay, and if p is equal to 1, that is going to be divergent because it's not strictly greater than 1. Okay, so that was a result we have a while ago. Maybe I just bring it up again so that you can refresh your memory. Okay, so P integral is like this. This one here, what's P? What does P equal to? P is equal to 1. So it's going to diverge to infinity. Okay, so diverge to infinity. And you can see that this corresponds to the area under the curve. Okay, so the area under the curve over here, that integral is actually diverge to infinity. Not just because this is an infinite strip. Okay? I remember, I think one student say, because this one here go to infinity, is an infinite strip, that's why it diverges to infinity. Not because of that. Okay? Because remember we have this. This is 1 over x squared, and the other one is 1 over x. Both of them behave very similar from 1 to infinity. Okay. However, this one here has a finite area under. The area under this is, we figured this out. I think it was 1, I think. Remember, it's 1. Finite area under is 1. But this one here, it diverges to infinity. Okay. Both of them here is an infinite, right? That happens when you rotate this and make it vertical. Okay. So if you have an infinite strip going up, it doesn't mean that it's going to be diverge to infinity. The area under that. Okay. So you have to actually investigate. Okay. So this one here diverge to infinity, which is this case right here. Okay. It corresponds to the area under the curve from 1 to infinity. Now, that harmonic series actually corresponds to those sum of those rectangle. The first rectangle here is 1, and here's 1/2, the area of those. And this is 1/3, 1/4, etc. Look at those rectangles. They are above. They're going to be above this area, right? This is going to be above this. So the sum of those rectangles is greater than the sum of all those areas under the curve, right? All those right there. But we know that what happened to this area in the curve? It diverges, right? It diverges to where? Infinity. Okay. So it diverges to infinity. Therefore, this one here has actual right here. Then it's going to be more than this. So also diverge to infinity. So the harmonic series diverge to infinity, as we already proved. Okay? So I show you 2 different ways to prove the harmonic series diverge to infinity. One is comparing to this integral. Okay, it's greater than this integral. And another one is using this, using the 2 to the n partial sum, and we show that it go to infinity. Okay, but you guys don't have to remember the proof. For you guys, you're responsible to remember this result. The harmonic series diverge to infinity. Okay, the next one over here is, we're going to introduce the theme called test for divergence. But before we do that, let's have this one. If the series is convergent, then the trend go to 0. Okay. I know that it might be a little bit hard for you to get used. I mean, it takes a while to get used to the notation. This one here is the series. What is a series? Series is, okay, let me write it down. That series over here is the sum. Remember, that's the sum. Okay. Okay. Remember, it's A1 plus A2 plus A3 plus, and continue this way. That's the series. If the series convergent, then what can we say about the trend? Then the trend is going to getting smaller and smaller and closer to 0. So the AN over here, then it has to go to 0. Okay, it has to go to 0. Does it make sense? If it doesn't go to 0, think about if you keep on adding something that doesn't go to 0, even though it's tiny, right? It was like positive. If you keep on adding that, like 0.001, you keep on adding 0.001, what happens? It gets bigger and bigger, right? If it's negative, like negative 0.5, you keep on adding that, it go to, it, then the series doesn't convert, right? Doesn't go to a finite number. So in order for the series to convert, then the trend that you add has to getting smaller and smaller and closer to 0. You're adding something really, really tiny, right? Okay. In order for the series to converge. Okay. So that was what the theme here said. So I put it, we phrase this right here. So if a series converge, then if n trend has to go to 0. If it's not going to 0, you're adding something that is not small enough, then the series is going to get bigger and bigger or smaller and smaller without boundary, right? So this is necessary for this series to convert. The trend has to go to 0. Okay? The proof of this is actually, I put it right here. Here's the idea of the proof. Okay, this is the idea of the proof. Okay. Now, have you guys learned about something called contrapositive statement? In Chinese called 逆反命题. Yeah? Yes. Gloria said, yes, I know 逆反命题. Okay. Okay. How does it work? Okay. So let me give you example. Okay. What is a contrapositive? Okay. So if you have, if a statement, if A, then B, this is a statement, right? What's the contrapositive? Contrapositive statement of this is what? If not, yeah, you got it. If not, what? If not, but you also reverse it, okay? If not B, then not A. Yeah, if not B, then not A. If not B, then not A. That's called contrapositive. And these two are equivalent. This and this, they are equivalent. Okay, they are equivalent. Okay. Can you give some example in real life? Some example in real life. Say, if you score, huh? Parent to the children? No, their parents and no. Okay, if don't have a parent, then you don't have the children. Yes. Okay, good. All right. Another example here is, for example, if you want to get an A, right? So then if you want to get an A, you need to score 90 and above. And if you don't score 90 above, then you're not going to get an A, right? So they're equivalent. Okay, it's the equivalent. Okay, so contrapositive statement are equivalent to each other. Okay, sometimes when you try to prove the statement itself, it might be hard. You can try to prove the contrapositive statement. It might be easier to prove. Okay, now go back to this one. This one, if this, then this. What's the contrapositive statement of this? If not this, then not this, right? If not this, that means if AN doesn't go to 0, then not this, that means the series diverges. So if AN doesn't go to 0, then the series diverges. Okay, you got it. Okay. So this is exactly what this thing says. So if AN doesn't go to 0, then the series diverge. And that's called the test for divergence because the result here says is divergent. Okay. So it is the test for divergence. Okay. Not a test for convergence. Okay. So which makes sense, right? If the trend doesn't go to 0, if you keep on adding something not smaller and smaller and getting closer to 0, then if you add them up, it's going to diverge. Okay, it's going to diverge to sometimes infinity or negative infinity, or sometimes it goes back and forth. Okay, okay. So if the trend doesn't go to 0, then the series diverge. Okay. Now, if you learn this from high school, you probably learned this in another name. It's called the entrance test because you're looking for the entrance. Okay. So if the entrance doesn't go to 0, then the series diverge. Another name for this is called divergence. Okay, so those are the different names for this. And I have a couple of notes over here. You can read that over. Okay, contrapositive, they are equivalent. Okay, sometimes if a statement is difficult to prove directly, we pull the contrapositive. Okay, the second one here is a common mistake many students make. Okay, some students try to pull the series converge using this test for divergence. They say, oh, if the trend go to 0, okay, so let me ask you, if AN, the N trend go to 0, does it show that the series converge? What happens if this go to 0? Is it guaranteed that series converge? It's just a simple question. What do you think? Jafar, what do you think? Ryan? You know, Ryan? If AN go to 0, is it guaranteed that the series here converge? Okay, Kimya say no. Kimya, can you come up with an example that AN go to 0 but the series diverge? I hear the music. Oh, 1010. Oh, but then if 1010, then AN is not going to 0. Okay, it has to go to 0. Did I say I just give you a hint? I hear the harmonic. I hear the music. Harmonic series. What do you think about harmonic series? What's harmonic series? Yeah, 1 over n, right? At this. Does the trend here go to 0? Does 1 over n go to 0? Yeah, it get closer and closer. 1 over n goes to 0 as n goes to infinity, right? Okay. The harmonic series, does it converge? Huh? It diverges to infinity, right? Okay. So the trend goes to 0 is no guarantee that it converge, but it's necessary for it to converge. Okay, think about that. Think about this. If you need to survive, you need to breathe in air, right? You need to breathe in air. But if you just breathe in air, it's not sufficient for you to survive. You need other things. Okay, so the trend over here go to 0 is just one of the things that you need for that to converge. You also need something else. Okay, so for example, if you need to come to school, you need to catch the bus, you also need to get up early, right? So it just getting up early, it's not necessary for you to come to class on time. You need some other thing to do, right? To guarantee that. So the train go to 0 is one necessary condition for the series to converge, but it's not sufficient. you know what was sufficient and necessary, right? So you need that, okay? So do not just say the series convert because the trend go to zero, okay? So again, I'm going to review this, the difference between sequence and series, okay? Sequence is just a list, right? The biggest number, like 1 to 3 is number, okay? Sequence is a sum, okay? So for series to converge, you need first, the trend has to go to zero. It is necessary. Without that, the series is not going to converge. But beside this one, you still need something else, okay? You need additional condition for the series to guarantee that the series converge, okay? So it's necessary. In Chinese, we call that 必要条件, but it's not the 充分条件, not the sufficient condition, okay? So just one of them. Okay, maybe we can try to see this one. Okay, let's try to use the test for divergence or the entrant test. I kind of like the name entrant test better because you focus on the entrant. Okay, Daniela, what did your teacher use for your school? They call the entrant test or test for divergence? Huh? Divergent test? Okay, called divergent test. Okay, all right. And notice the result for the test for divergence is a series divergence. Okay. Okay, let's look at this one. Okay. Do you think this series here converge or not? Okay. Okay, that's a guess. Okay. All right, let's think about the entrant. Okay. Let's look at the entrant. The entrant is n squared over 5n squared plus 4, right? Do you agree? Okay. As n go to infinity, what does it go to? Use a shortcut. Use a shortcut. And n to infinity, focus on the dominating trend over there. Yeah. So Gloria said it's 1 over 5. Do you agree? Yes. Okay. So it goes to 1 over 5. Okay. So we focus on this dominating trend. Okay. So looking at this and this. So it's 1/5. Okay. And which is not 0. Okay. What does the entrant test say? So if the trend doesn't go to 0, what can we say about the series? It diverge, right? Think about if you keep on adding something that's 1/5, 1/5, 1/5, 1/5, right? If you keep on adding 1/5, 1/5, okay, then the series is going to diverge, okay? Because in the long run, the trend is getting very close to 1/5. So it seems like you keep on adding 1/5, 1/5, and you keep on adding that, then the series is going to diverge, okay? Yeah, you got it. Good. By the test for divergence, or you can say the entrant test. Okay. Okay, the next one, I want you to try this. Renata, what do you think? AN. I'm looking at the entrant, right? So let's look at the entrant. Is the entrant here going to 0 as n go to infinity? What does it go to? Okay, so Kenya say power 2. Do you guys remember? For inverse tangent, right? But what's the graph for inverse tangent, right? So the graph for inverse tangent looks like this way. That's inverse tangent of x. And as x go to infinity, okay, it's going closer and closer to pi over 2 right here, right? Getting closer and closer to pi over 2. Okay, so that's equal to pi over 2, which is definitely not 0, right? Mm-hmm. So if the n-term doesn't go to 0, what can we say about the series? It diverges, okay? Think about if you keep on adding something that is close to power 2, right? Something that's close to power 2, keep on adding that. Certainly the series is not going to sum up to a finite number, right? So yeah, so like that. So the n-term test is kind of convenient to use because you just look at the n-term, right? Okay. The next one here. Okay, we're almost done. Now you see 110B is hard. But it's doable, okay? Told you. I warned you guys, okay? A lot of things, okay? Determine this, whether the series is convergent or divergent, okay? Looking at this, how about we separate them and investigate, okay? Let's separate them into the sum of 2 series. Was it a 1 or 2? Oh, I just changed it. I changed it into a 2. Okay, let me change this. Let's make it into a 2. Just make it easy. Okay. Okay. So I have this series over here. I break it into the sum of 2 series. Okay. This one. Like that. Okay. Focus our attention on the first one first. Okay, let's do the first one. This first one right here. This one. And if you have hard time to get a feel of how this look like, you try to write out the first couple terms. Okay. So the first one, you substitute index here to be, remember this is to the n power. Okay. And go from 1 to infinity. So you substitute 1 in it, you will get 1 over e. Substitute 2 in here, you get the square, then third, and etc. What kind of series does it remind you? What do you call this? What category? Diago? Okay, there's only a couple choices, right? What did we learn today? Geometric? Telescoping? Harmonic? Geometric. Okay, so Angela say geometric. Do you guys agree? Danny say. What do you think, Danny? Danny say whatever Angela say.
Probably wrong, so I would disagree.
Okay. How about or yeah. Okay, yeah. What do you think? Is it a geometric series? You're not sure? Okay. Okay, let's
I'm also not sure.
Okay. Huh?
Harmonic?
Harmonic? Huh? Harmonic? Okay. Okay. What's harmonic? Okay, let's review a little bit. Harmonic. What's harmonic? Okay. Harmonic is this series, right? 1 over n. And if you write it in the long form, that will be what? 1 plus 1/2 plus 1/3 plus 1/4. Now, does it look like a harmonic now? No, this doesn't look like harmonic, right? Okay, and then Angela say geometric. Okay, let's review geometric, okay? Geometric. Okay, how does geometric series look like? It's going to be a times what? R to the n minus 1 or n, right? N minus 1 or n, okay? And if you write out the terms, so that will be the first one, say n here go from 1 to infinity, so that will be what? A plus a times r, right? And then plus a times r squared, etc. Okay. Now, you actually write this comparing this one with this one. do you think is geometric right now? If we put them close to each other. Yes, yes, right? What is R in this case? Yeah, is this. Remember, it could be n minus 1 or n, okay? So this one here, n minus 1 or n, okay? Either way. Okay, so in this case, R is 1 over E. You got it. It's 1 over E. Now, if you're still not sure about this, you wrote that down, right? You wrote down the first couple terms. From one term to the next, what do you multiply? You multiplying 1 over E, right? You keep on multiplying 1 over E. So it's 1 over, so you keep on multiply a common ratio. So definitely this should be a geometric series, right? Yeah. So Angela, you got this right. So you have to stick with that. Yeah, you should believe in yourself. Okay. All right. Good. So indeed it's a geometric series. Okay. So it's a geometric series. Now, is convergent or divergent? What do you think?
It's convergent.
You think it's convergent? Why?
Because it's a finite number.
How do you tell a geometric series converge? It converge when R is what?
Oh, between negative.
R is between -1 and 1. So it converged, right? Okay, for geometric series. So for geometric series, if R is between -1 and 1, it converges. So let's take a look at 1 over E. Is 1 over E between -1 and 1? Yeah, 1 over E definitely is between -1 and 1. So therefore the series converge or diverge. It converge, and we also know what does it convert to. What does it convert to? What does it convert to? Kieran. Yeah, you got it. But which formula you're using? Tell the class how did you figure this out? Yeah, so if the geometric series here converge, it's going to convert to the first term over 1 minus the common ratio, right? Yeah, you got it. So when you converge, you actually convert to the first term over the common ratio. In this case, it is 1 over E. The first term is 1 over E, right? Okay. And the common ratio over here is 1 over E also. So how do you simplify this? You multiply up and down by E. Okay. You multiply up and down by this denominator. This is 1 and this is E minus 1. Okay. So that series here converge, and we also know what it converts to. Okay, let's look at the second series. Okay. So we're going to take a guess here. This one. Okay, the green one. Okay. What is it? Well, I think we did something similar to this, right? Did we use partial fraction decomposition? Right? And decompose this into what? I think, yeah. So we take out the 2. Okay. And it, wait, hold on. That was not so fast. Okay. What kind of series was that? Telescoping. Oh, you saw it. Okay. It's a telescoping series. We found its sum, right? We found the sum. Do you remember what's the sum of that telescoping series? Was it 1? Yeah. It is 1. Okay. That's equal to 1. Okay. Okay. So therefore, it's going to be 2 times 1. So that converts to 2. Okay. So the telescoping series. So far, we only know two types of series that you know exactly what they're equal to. Telescoping series and converging geometric series. Okay. Then after that, you can just add them up, right? So this one convert to 1 over e minus 1. This convert to 2. So it's going to convert to this plus 2. Okay, so that's the result right here. Okay. Okay. Now, we're almost done. Okay, I was trying to give you hope. Okay. Okay, almost done. Okay. Suppose that we know this series converge. Okay, notice that this series here converge. And what can we see about a series that start from n equal to 1? What's the difference between this one and this? This one start, the change is start from n equal to 1. This change here, the change start from n equal to 5, right? If I know this one converge, what can I say about this? Converge, okay, yeah, good guess, okay. What's the reason? Okay, let's think about it. So you can relate this one with this one by adding the first one in front, right? This one starts from n to 5, so you can write down the first one change in here. So I don't care what that is, but let's just put A1, A2, A3, A4, okay? Now we know that those are finite numbers, right? Those are just numbers. If you sum this up, would that be a finite number? Sum of number here, sum of 4 number will be finite number, right? Okay, so certainly it's going to be a finite number. And what do we know about this part here? It converges, right? What is convergence? Converge means is equal to a finite number. So a finite number adding a finite number, would that be a finite number again? Yeah, so it's a finite number. So that shows that if this one converges, then this one also converges. Okay? So what does it that's the important remark is this. So the tail of the series is the one that we need to determine if the series converges or not. Because the finite number change in front is going to add a finite number anyway. So the tail over here actually is going to affect the series converge or not. So a series converge you can only if any of its tail converge. Okay. So you can ignore the first and change and start from some index on and look at the top. If this top converge, then the series converge. If this one diverge, then the series converge.